Hi, everyone. In this video, I'm going to be covering the section P.1 classwork problems. So there's 4 problems I want to work through. But before we get into those problems, I just want to briefly talk about this class in general. Precalculus, the focus of this class is algebra, right? We call it precalculus because it's a preparatory class for calculus 1. But the language we're speaking in this class is the language of algebra. And there's 3 main fundamental objects that we're going to be working with throughout the entire semester. We have expressions, we have equations, and we have functions. Each of these are similar and related, but each is fundamentally different. So an expression is any object, any term that contains numbers, variables, and mathematical operations like pluses, minuses, times, divides, square roots, exponents, things like that. So for example, an expression, something like, let's say 2x squared minus 7 plus x, right? There's no equal sign. That's the key. Expressions do not have equal signs. There's nothing to solve for. We cannot solve for x because this expression that I just wrote is not equal to anything. So questions that you may see in the homework or the quizzes or the exams that involve an expression, 2 of the most common keywords you're going to see would be evaluate and simplify. Right? The word evaluate, another word for that is replace. Right? So you may see a question that says, evaluate this expression. So let's say evaluate for x equals 3. So what that means is we replace the variable x with the number 3. So we'll have 2 times, instead of x to the second power, it'll be 3 to the second power, minus a 7, and instead of plus x, we'll have plus 3. So this is an example of an evaluate problem. Now we would perform these operations. Exponents first, so 3 times 3 is 9, so that's 2 times 9 minus 7 plus 3. 2 times 9, multiplication comes next. 2 times 9 is 18 minus 7 plus 3. And then we have addition, subtraction. We could just go left to right. 18 minus 7 is 11. And then if we add 3 to that, we get 14. All right, so that's just an example. The word simplify, another key word there would be combine like terms, all right, which we'll see that later. An equation, an example of an equation would be something like 2x plus 1 is equal to 13. All right, 2x plus 1 equals 13. So now we can solve for x. Figure out what number do we have to replace the x with so that the left-hand side is equal to 13. Right? A variable is a temporary placeholder. It's a temporary placeholder for a number. You don't know what that number is yet. The keyword yet. Right? So we have to figure out what x is holding the place of. All right, so we could solve this by removing the 1 and the 2 from the left-hand side. And the way we do that is to apply the opposite mathematical operation. So if we want to get rid of a plus 1, we need to throw in a minus 1. So plus 1 and minus 1 cancel. So if we subtract 1 from the left-hand side, we get just 2x. But the most important rule of algebra, is when you're applying some change, some operation to a mathematical equation, an algebraic equation. You could do anything you want to one side as long as you do the same thing, make the same change to the other side. So if I subtract 1 from the left, I got to subtract 1 from the right, and that'll give me 12. So now we have, we're one step closer to getting x by itself. Right now, x is being multiplied by 2. So we could eliminate that or cancel that out by dividing by 2. Times 2, divide by 2, cancel because 2 over 2 equals 1. So that'll give us x by itself. Right? And whatever we do to the left, we have to do to the right. Or whatever we do to the right, we have to do to the left. Since we divide the left by 2, we have to divide the right by 2, and 12 over 2 equals 6. So there's our answer, and that means that 2 times 6 plus 1 equals 13 is true, right? That's what it means to be an answer. So x equals 6 was the answer, because if you pop in a 6 for every x, you get a true statement. And then finally, functions. We'll deal with functions later. I'm not going to talk about functions in this video other than just saying the notation. So a function will have the notation f of x, f parenthesis x, is equal to 2x plus 1, or instead of f of x, sometimes we'll see the letter y equals 2x plus 1. All right, we'll get to functions in later sections. Okay, so moving on to the classwork problems. So problem number 1, evaluate the expression 2x plus y divided by x times y minus 2x for the values x equals -2 and y equals 4. Okay, keyword here is evaluate. Remember, evaluate. Another word for evaluate, replace. All right, so we're going to replace every x with a -2, and we're going to replace every y with a +4. Right, that's what it means. That's what it means to evaluate an algebraic expression. So let me go. I wanted to use blue here. 2x plus y divided by x times y minus 2x. Okay, so 2 times x. All right, instead of x, we're throwing in a -2. Plus y, instead of y, we're plugging in a 4. All right, replace every x with the -2, replace every y with the 4. So x times y would be -2 times 4. We're saying x is a -2, y is a 4, so we get -2 times 4 minus 2 times x. So we'll put in another -2. All right, so this was an x, this was an x, this was an x, right? This was a y, and this was a y. So let's combine our our numbers. We'll perform the operations. We'll multiply, we'll add, we'll subtract, we'll divide. So on top, we've got 2 times -2, which is -4 plus 4. On the bottom, we've got -2 times 4. That'll be a -8 minus 2 times -2, which is a -4. So on the bottom, we're subtracting a negative, which means we're adding. So on top, we get 0, -4 plus 4. On the bottom, -8 minus a -4 is -8 plus 4, which is -4. And 0 on top is fine. You're not allowed to have a 0 on the bottom of a fraction, but 0 on top, that's perfectly fine. 0 divided by -4, or 0 divided by anything, is 0. So that's our answer. If we plug in the -2 and the 4 for the x and the y, this becomes 0. All right, number 2. So different topic altogether. Sets, set notation. So a set, the mathematical notation for a set is a group of objects. Normally they're going to be numbers or variables or a combination of numbers and variables, but they could be anything. Words, shapes, anything. The notation we use for sets are these sort of squiggly brackets. These are called set brackets. These are called set brackets. And so we have two sets. We have set A, which is a 1, a 3, and a 7. We have set B, which is a 2, a 3, and an 8. And what we want to do is find what's called the intersection. So I have the first definition down here is that symbol. It's up, that's sort of an upside down U. Means intersection. The intersection of two or more sets is the set of all elements, in this case, elements are numbers, that appear in every one of the original or individual sets. So the key word for intersection is overlap. Where do these two sets overlap? Right, so A intersect B is equal to the set of, right? When you see that first, the way you read that, the squiggly set bracket is the set of the overlap between the two sets. What do these two sets have in common? Well, number 1 is only in set A. 3 is in both sets, so there's an overlap there. The 7 is only in set A. The 2 is only in set B. The 8 is only in set B. So the only number that appears in both sets, or where the two sets overlap, would be the number 3. The next symbol means union. And that's definition 2 down here. The symbol thing that looks like a U means union. And the union of two sets is the set of all elements, again, in this case, numbers, that appear anywhere in any set. Could be in the first set, or could be in the second set, or it could be in both sets. In this case, anything that appears anywhere would be, so we'll say A union B is equal to the set containing, normally we put numbers in numerical order, smallest to largest. So anything you see up here between the two sets, there's a 1, there's a 2, there's a 3. Actually, there's a pair of 3s, but we only need to give each number once in the union. So there's a 1, a 2, a 3. I see a 7 and an 8. Any number that appears anywhere in those two original sets. Okay, so that would be the union. The union's never smaller than the intersection. All right, number 3. Now we have a different type of problem here. Identify each number from the set. So we have -9, -4/5, 0, 0.25, the square root of 3, 9.2, and 100. Okay, so we have the natural numbers are all the positive whole numbers. 1, 2, 3, 4, and that ... means you continue that pattern forever. So 1, 2, 3, 4, 5, 6, 7, 8, ... Right? The next set out from there would be the whole numbers. So that's just the natural numbers, which is this. This is the natural numbers plus the number 0. So if you include the 0, you get the whole numbers. Next, we've got the integers. So the integers contain the natural numbers. 1, 2, 3, ... Also contains the whole numbers. But in addition to that, also contains the negative whole numbers, -1, -2, -3, and there's a dot, dot, dot going to the left because the negative numbers get smaller and smaller. Next, we have the rational numbers, the set of all fractions. Right, so I have this written a little bit differently. I have it using set brackets. So the set of all fractions, a over b, where a and b are integers. And also, b can't be 0 because you can't have a 0. Ooh. You can't have a 0 on the bottom of a fraction. So integer divided by integer as long as the bottom is not 0. No, I next to real numbers, you see a blank there. So we have this another set that you might see in the homework. I didn't include it on this problem, but it might come up. The irrational numbers. An irrational number is basically numbers that are not rational. And finally, the real numbers. This is basically all numbers you could see or that could be used to express a value or an amount. So the real numbers would be the rational numbers union with the irrational numbers. Okay, so if you take all the rational numbers and all the irrational numbers, so an irrational number would be a number that you cannot write as a fraction of whole numbers, of integers. Right, the irrational numbers are a little bit intuitively more complicated. So like a square root that doesn't simplify. So like, for example, up here, you see the square root of 100. Well, that's a natural number because if you take the square root of 100, you get 10. So the square root of 100 is 10, which is positive whole number, so it's natural. But the square root of 3, well, we can't simplify that at all. And if you plug in the square root of 3 into a calculator, you'll see a decimal that just goes on forever. Right? So the square root of 100 would be a natural number. The square root of 3 would be an irrational number. Okay, so let's go through this list. -9. Right, where is -9? Well, it's not a natural number because it's negative. It's not a whole number because it's negative. It's an integer because it's a negative whole number. It's also a rational number because you could write -9 as a fraction. -9 could be written as -9 over 1. So every whole number, every integer, positive or negative whole number, can be written as a fraction by writing it over 1. Okay. And so if it's a rational, if it's rational, it's also real. Right? The natural numbers are inside of the whole numbers. The whole numbers are inside of the integers. The integers are inside of the rational numbers, and the rational numbers are inside of the real numbers. Okay, next one, -4/5. Not a natural because it's not positive whole number. It's not a whole number because it's not positive or 0, it's negative. It's not an integer because it's a fraction. It is a rational number, -4/5. And if it's rational, again, it's also real. All right, let's just keep going through the list. The next number is 0. There's no 0 here in the natural number, so it's not a natural number, but it is a whole number. And it's also an integer. If it's a whole number, it's an integer. If it's an integer, it's rational. If it's rational, it's real. So 0 would be part of 4 of those sets. Okay, now we got a decimal. So the thing about a decimal like this, 0.25, the 2 is in the 10ths place, and the 5 is in the 100ths place. So 0.25 can be written as 25 over 100 because it's a decimal that stops at the 100ths place, which means it's divided by 100. And 25 divided by 100, we could simplify that to 1/4. So 0.25 means the same as the fraction 1/4. So where would 1/4 go? Because 0.25 and 1/4 are the same number. So where would 1/4 go? Well, it's not natural. It's not whole. It's not an integer. But it is rational because you can write it as a fraction. 0.25 can be written as a fraction, and if it's rational, it's also real. Okay, square root of 3, already talked about that one. That is an irrational number because it's a square root that doesn't simplify. So I'll put an answer here for irrational numbers. That would just be the square root of 3. And that's the only irrational number up there. Some other irrational numbers would be like the number pi or the exponential number e, which we'll see later on in the semester, maybe chapter 3 or so. We got another decimal, 9.2. Well, the decimal, just like the 0.25, 9.2, it's a decimal that stops in the 10ths place, so it's being divided by 10. So we have 92 divided by 10. We could simplify that or reduce that. I think 46 divided by 5. It doesn't matter that we reduce it. What matters is that we know that the 9.2 can be written as a fraction. Okay. So 9.2 is not natural, not whole, not an integer, but it is rational. And again, if it's rational, it's real. And then the square root of 100, already talked about this one. The square root of 100 is the same as the number 10. And it's a positive whole number. So what that means is it's a natural number, square root of 100. That's the only one up there that was natural. If it's natural, it's also whole. If it's whole, it's also an integer. If it's an integer, it's also rational. And if it's rational, it's also real. Okay, so we use the fact that, let me just put this up here so we have it, -4 over 5. Oh, no. What was the 0.25? 0.25 is equal to 1/4. We use the fact that 9.2 is equal to 92 over 100. And we use the fact that the square root of 100 is equal to 10. Okay, a lot of parts here. So it took a little while to walk through this problem, but that does it for number 3. And the last one, we have some absolute value notation here. The absolute value operator, also called the distance function, because in real life, in the physical world, distance is always positive. It could be up, it could be down, it could be left, it could be right. You could call it negative, but that doesn't mean it's a negative distance. Negative in the physical world means either down, so positive up, negative would be down, or positive is forward, negative is back, but it's still a positive amount. So it gives a distance from a number between a number and 0 on the number line. So let me actually draw a number line here. So at the center of our number line, we've got 0, 3. We'll go to -6. This number line keeps going forever, right? So we've got two numbers here. We've got 2. Oop. We've got a 2. And that's a distance of 2 units or 2 steps from the number 0. So the absolute value of x, we're evaluating, so we're replacing, we're plugging in a 2 for x. So the absolute value of x is equal to the absolute value of 2, which is 2. Then we've got another number. Let me use a different color here. I'll use green, -5. So over here. Well, that's 1, 2, 3, 4, 5 steps or 5 units away from 0. It doesn't matter which direction. It's just a distance of 5 units from 0. So the absolute value of y for this problem is the absolute value of -5, because we're told that y is equal to -5, and that's equal to +5. So the absolute value of x plus the absolute value of y is equal to 2 plus 5, which is equal to 7. So we could think about this in a slightly more informal way. The absolute value of a number is, well, it's itself. If you start with a positive number, the absolute value of a positive is positive. If you start with a negative, the absolute value of negative is also positive. And since the absolute value is the distance from 0, if we take the absolute value of 0, in that case, we get 0. All right, that's it for classwork problems, section P.1.